So we're going to discuss in this video radical expressions and equations, and actually it's kind of the title of the unit, but we're not going to discuss them all in this video. We'll do it over a series of videos. So what we want to do first, as we look at radical expressions and equations, is to figure out what exactly do we mean when we talk about a radical. So when we look at parts of a radical, you have, first of all, the identifier. The big identifier is the radical sign. If you don't have a radical sign, you don't have a radical. If you do have a radical sign, you know you have a radical. So this is sort of the defining feature that identifies, okay, we have a radical, which is probably fairly obvious. But up here in this area, you will sometimes have a number. You don't always have a number, but you might. So the index of the radical is the number that tells us what type of root we're taking. You're used to square roots, so you would say, yeah, I know the square root of 81 is 9. You may have seen cube roots. So the cube root of 27 is 3, for example. You might have seen that. That's probably the highest you've seen, but the index could be anything. It could be 4 or 5. All right, you're allowed to have any sort of index. And all that's telling us is we want the 4th root or the 5th root. Okay, and again, sort of looking backwards, is what that means is what raised to the 4th power gives me the number that's underneath the radical. And the number that's underneath the radical is called the radicand. Okay, so it's the number that you're actually taking the root of. So you have the index that tells you the type of root you're taking, and then you have the radicand, which is what you're taking the radical of, all right, or the root of. Now, there are two types of radicals. There are entire radicals, which means that everything is underneath the radical sign. And then there's mixed radicals, and mixed radicals have something outside of the radical sign and something underneath. So that has a radicand, but on the outside of the radical, there is another term, and it may be just a coefficient like 3. It could be an expression like 3x. Okay, but it's a mixture. That's why it's called a mixed radical. It's a radical and then times something that's not underneath the radical sign. So what we want to be able to do is discuss how do I convert from one to the other. And essentially what we're doing with an entire radical going to a mixed radical, which is what we're going to discuss first, is we're trying to simplify. Okay, that's what we're trying to do. So when you look at converting entire radicals to mixed radicals, there are basically two ways to do that. Okay, the first method is to use the greatest perfect square, and I'm going to just say this is perfect square if it's a square. So it could be perfect cube, okay, if it's a cube root, or 4th, and so on, all the way up. But we're going to try to look for the factors of the radicand that actually are perfect whatever root, okay, perfect squares, perfect cubes, and so on. So here's an example. We have the square root of 200, sorry, and we're looking for what are the perfect squares because it's a square root. So we look at the perfect squares and we know the perfect square factors of 200 are 1, 4, 25, and 100. The biggest of those is 100. So what we do is we write 200 as the product of 100 and 2. So we just write it as the square root of 100 times 2. And then we split the radical. So we say it's the square root of 100 times the square root of 2. And then we take the square root of 100 because we know that that's nice. It's 10. So that's using the greatest perfect square factor method. That method is fairly efficient, but you have to know your perfect square factors and you have to know which one's the greatest perfect square factor. Okay? If you look at the other method, the other way of doing it, you can use what is called prime factorization. And you may not recognize this right away, I don't know, but what prime factorization does, and I'll just put here, is it takes 200 and it's put into its prime factor. So it's 2 is a prime number, so we're taking 2 out each time until we can't anymore. And then we look at 25 and notice that it is 5 times 5. So the perfect, the prime factorization, sorry, is this. It's 2 times 2 times 5 times 5 times 5, which is where they're getting that from, okay, in case you're wondering what just happened. And then what you look at is how many groups of identical factors are there. And in this case, we want the group size to be 2. In other words, we want something squared, right? Because we have a square root. So we look at 2's, the 3 2's that are there, and we notice that we can group 2 of them. And then we have 1 left over. We have 1 that's kind of left out. And then the 5's, there's 2 of those. So we can group them as a 5 squared. then we take the square root of the stuff that's squared. So in other words, we take the square root of 2 and squared, and we take the square root of 5 squared, and we put those out front. So we have 2 times 5 times root 2. That root 2 is coming from this 2 that's left there. Okay, and then we finally get 10 root 2. So there's two ways to do it. My suggestion is the greatest common factor method, the first method that we talked about, is quicker, but it's prone to problems if you find a perfect square factor or a perfect cube factor or whatever the case might be that's actually not the biggest, the greatest perfect square factor. Then you might have to do it more than once. Okay, you may find that you actually have to reduce 2 times. The prime factorization method is going to give you the answer every time, but it does take a little bit longer because you have to prime factor first. So it's up to you how you go about it. But we'll look at a couple of examples, and I'll kind of intersperse the method so you can kind of see examples of each one. All right, so if we look at some examples, the square root of 78, we'll do this one with the greatest common factor. So when we do that, we're looking for perfect square factors of 28, and we know that 4 times 7 is 28. So 4 is the biggest perfect square. So then we take the square root of 4 times the square root of 7, and we finally get 2 root 7. Okay? Square root of 56, we'll do this with the prime factorization method just to show you. So 56, we take 2, and it's 2 times 28. 28 is 2 times 7, sorry, times 14. I'm jumping ahead of myself, and then it's 2 times 7. Okay? So this, the prime factorization, becomes 2 times 2 times 2 times 7. And then that gives me the square root of 2 squared times 2 times 7. We take the square root of the 2 squared, that becomes 2, and then it's root 2 times 7, which is 14. That's what's left. So 2 root 14, that's how it simplifies, okay? And this is 2 root 7. And again, you can use, instead of using prime factorization, you can use the greatest common factor or vice versa. I just showed you a couple of examples of each, right? With 32, the greatest common factor that's a perfect square is 16. Not the greatest common factor, but the greatest perfect square factor. And this is 16 times 2. So then we're going to get 4 root 2 because the square root of 16 is 4. Okay? For 128, again, we can prime factor just to show you how this works. I'm not suggesting that it's the best method necessarily. Okay, but what we're going to do is we're going to keep dividing by 2 until we can't anymore. And then we will do something else, but this looks like it's just going to keep letting us divide by 2. So what we end up with is 2 times 2 times 2 times 2 times 2 times 2 times 2. And what I'm going to do is, instead of writing all those out, you'll notice it's really just 1, 2, 3, 4, 5, 6, 7 2s. So I'm going to get 2 squared 3 times. That'll give me 6, right? And then times 2. And that means I get 2 times 2 times 2 square root of 2. And that gives me 8 root 2. So that's how we use the prime factorization method. Okay, I'm going to leave the other 2 for you to try on your own. Actually, there's 4 there, but you can try them on your own and see what you get. But that gives you an idea. Okay, and again, I'm giving you 2 examples of prime factorization and 2 examples of the greatest common factor. You can use the greatest common factor for all of them. Okay, which in this case, if you look back here, just for a second, greatest common factor, that's the perfect square. And again, I keep saying common factor. It's not really the greatest common factor. It's just the greatest factor. That's a perfect square. Is 64. So if I did square root of 28, the other way of doing that, just to clarify for you, if you're not sure, would be 2 times 64. And then that's root 2 times root 64. And the square root of 64 is 8. So we get 8 root 2, which is the same answer that we got here. So you can get the answer either way. Either method works. Now, what happens when we throw in variables? Okay, because that is another possibility. Or what happens when we change the index? So you notice now I've got an index here that's 3 and an index here that's 4. So we have to look at a couple of things when we're doing this. The first thing is when we look at this one and any square root, you're going to look at the numbers the same way. So I'm going to split 18 into 9 times 2, okay? But what I'm going to do actually is leave a little bit of space, because what I want to do is actually also split the x into its perfect square factors, okay? So I'm going to have 9, and then x cubed is going to be x squared times x. So I'm going to get this, okay? Basically, with the variables, you're looking for a power of 2, right? Because when you take the square root of something squared, it just becomes itself. So now I take the square root of 9x squared, and I get 3x, and then I'm left underneath with root 2x. Okay, so that's how I would split that. If we look at this one, 12x squared y, I'm going to split that. 12 is 4 times 3, okay? X squared is a perfect square, so I'm going to write it as a perfect square, and then y is just by itself, so just leave it like y. We can't make it a perfect square because it isn't one. And essentially all you're doing is looking in the powers, you're looking for multiples of the index, okay? So in other words, if it's a square root, I'm looking for powers of 2. If it's a cube root down here, which it is, I'm looking for powers that are 3. I'm looking for roots of 3 for the variable, okay? And then we take the square root of 4x squared and get 2x, and then it's square root of 3y, and that's my answer, okay? Here, I'm doing a cube root, so a little bit different. I'm also a little bit different with my number, because I'm not looking for a perfect square now. I'm looking for a perfect cube. And you may not know your perfect cubes as well as your perfect squares. But your 1 cubed is 1, 2 cubed is 8, right? 3 cubed is 27, 4 cubed is 64, I think. And then you keep kind of going from there. So what you end up with is big numbers, okay, fairly quickly. So with the cube roots, you're looking for a perfect cube, but you don't have to know as many because they get too big pretty quickly. So we'll notice that 16 is a multiple of this perfect cube, okay? It's 8 times 2, so 8's the perfect cube, 2 is going to be left here. And then we're splitting x to the 6th into groups of 3, so this actually is 2 groups of 3, so we can leave the x to the 6th. And what we do is we divide that by 3, okay? So we get the cube root of 8 is 2, and then 6 divided by 3 is 2, so we have x squared. And then what's left is the cube root of 2, okay? So that's our answer. With the fourth root, it's the same thing, except you're looking for perfect fourths now, okay? So you have to kind of think, well, what's my perfect fourth? Well, 1 is 1 to the fourth. 2 to the fourth is 16. 3 to the fourth is 81. And you're already bigger than 80. So you know your options are either 1 or 16. So we're going to try 16. And it's going to be 16 times 5. That's what 80 is. And then the fourth root of 16, this is where this gets a little bit different. The fourth root of 16 is 2, so it becomes 2 fourth root of 5. Yeah, you just have to be careful with that, because sometimes we get into the habit of doing square roots so much that we think we're still taking the square root. We're not. We're taking the fourth root. So the square root of 16 is 4, but the fourth root of 16 is 2, and that's what we're looking at. Okay. If you look at the square root of 4y, I actually don't have to do any work here, because the square root of 4 is 2, and I can't do anything with the y, so it's just 2 root y. And then here, again, we're doing a cube root. So the cube root of 125 is 5. 5 cubed is 125, and then we just have the cube root of y squared. So there's our answer, okay? And that's it. So that's how you work from entire radicals to mixed radicals. Okay, again, we'll just do a couple more here. We already know the square root of 200 because we already did it. So it's 10 root 2. These are from your textbook. But this is fourth root of c to the 9. What you're doing when you're doing a fourth root, you're looking for multiples of 4 then, right? So we're going to split 9 into 8 and 1, and then 8 divided by 4 is 2. So it's c squared and then fourth root of c, okay? And then for 48, that is 16 times 3. And then y to the 5, we're looking for multiples of 2. So we're going to use 4, and then we'll have a y left over. So the square root of 16 is 2. Sorry, the square root of 16 is not 2. The square root of 16 is 4. And the square root of y to the fourth is y squared. And then we have left 3y. Okay, so it's 4y squared, square root of 3y. So that's how you switch from entire to mixed. Okay, now the question then is, how do I go backwards? And actually going backwards is much simpler, because all you do is raise whatever is out here to the index and put it in there. Okay, so for example, it's 7 on the outside. So you raise it to the index, which is 2, and you write underneath. It becomes 7 squared. Okay, and then you just multiply them together. So you make it root 2 times 7 squared, and then that's 49 times 2, and so you get the square root of 98. Okay. Same thing with the second one. The second one, we're going to go a to the fourth squared times a. So just to do that over here, I'll show you the solution in a second. But you're going to have the square root then of a to the fourth squared times a. And a to the fourth squared is a to the 8th, if you remember your exponent laws, times a. And that gives you the square root of a to the 9. Okay? And then the last one is a cube. So for this one, you're going to write this as the cube root of, and then it's 5b cubed times 3b squared. Okay? And 5 cubed is 125. Get this out of my way. And b cubed is just b cubed. So you're going to get the cube root of 125b cubed multiplied by 3b squared. And if you do that, you get the cube root of 125 times 3 is 375. And then b to the 5th, because you're multiplying, so you add the exponents. So that's my answer. Okay, and again, you can see the solution here as well. But that's how you do that. So a mixed is much easier. So all we're going to do here is to show you, we're going to take the square root, and then we're going to write the 4 as squared times 3. And that's the square root of 16 times 3. And that's the square root of 48. So pretty simple. 5 root 12, we're going to have the square root of 5 squared times 12. Okay, 5 squared is 25, so we're going to get 25 times 12, which is 300. So we get the square root of 300. Okay, when we're doing cube roots, same thing, but we're cubing what's on the outside. Minus 3 cubed times 6. Minus 3 cubed is minus 27. So we get the cube root of minus 27 times 6. Okay, and that's 120 and 42, so it's 162. Okay, here you have a fourth root. So again, we're just going to take the 3 and raise it to the index of 4, and that's going to give me 3 to the 4th times 5. 3 to the 4th is 81 times 5, and that's the fourth root then of 405. Okay, so hopefully you're getting the hang of that. It's much easier, I think, than going the other way around. There's a bunch of other examples here. We'll just do one of them here. It's 2x and then the cube root of 5y squared. So that's going to become the cube root of 2x cubed times 5y squared. And then that becomes the cube root of 2 cubed is 8. So we get 8x cubed and then times 5y squared. And then that becomes the cube root of 8 times 5 is 40. And it's x cubed y squared. And that's my answer. So you can do the other three on your own, but that's the idea behind mixed radicals becoming entire radicals, okay? And there's just a bunch of practice here for you to try. So that's going to be included in the notes you're given, and I'll leave the video there because we're going to get into adding and subtracting after that, and we'll do that in the next video. So you can just practice these if you want to look at them, and then You can find the solution from your teacher.